Okay, in today's lecture, we're going to cover the second part of the section 6.2 material on line integrals. So in the first part of this section, we had defined a line integral of a function of 2 or 3 variables evaluated over a space curve or a plane curve C. And we saw that to evaluate them, we want to express our curve in terms of parametric equations, and we can convert our line integral with respect to arc length to a line or to an integral of a function of t. There are other types of line integrals which we have not yet discussed for a function of 2 or 3 variables. So let's start by defining them here. The other types of line integrals which we will sometimes work with in this course are called the line integrals of our function f along a curve C with respect to x, y, or z. So these line integrals are a little bit different from the line integral that we had worked with before. So here, the line integral that we were working with before would be like the integral over some curve C of the function f of x, y, and z. And then we were using ds, the differential of arc length on the end. Here, we could use the differential dx. We would call this the line integral of f over the curve C with respect to x. And if we have parametric equations for the curve C, we would replace the values of x, y, and z in our function with their parametric equations, x, y, and z of t. And then the differential of x would be given by x prime of t dt. So here recall that if we have a function, x is given by x of t, then the differential of x is defined as the derivative of x, that is x prime of t times the differential of t. So that dx term on the end is now given by x prime of t dt. When we were talking about the line integral with respect to arc length, that differential of s was the square root of a sum of squares of x and y prime. Here it's a little bit different. Now similarly, we could define the line integral of a function f of x, y, and z over a curve C with respect to y as the integral with respect to t over whatever our parameter interval is, say a to b, where x, y, and z are replaced by the parametric equations for that curve, and the differential of y is then given by y prime of t times the differential of t. This would be the line integral with respect to y. And then lastly, we could define the line integral of our function over the curve C with respect to z as an integral in terms of the parameter t, where x, y, and z are replaced by the parametric equations for x, y, and z. And then the differential of z is replaced by z prime of t dt. So the line integral that we had initially defined in the first part of this section, where we have a ds, is referred to as the line integral with respect to arc length. So we would say that for distinction from the line integral of our function with respect to x, y, or z. So let's look at an example of evaluating a line integral of a function with respect to these other variables. So in this next example, we're asked to evaluate this line integral of x times y with respect to x plus x minus y with respect to y over the curve C, where C is defined to be the arc of the curve x equals y to the fourth, that moves from the point 1, negative 1 to the point 1, 1. So let's visualize this curve to start with. Here we have some curve in the xy plane. And it's the arc of the curve x equals y to the fourth. So it's sort of similar to x equals y squared. It's like a parabola opening along the positive x-axis, a little more steep for larger values of y. And we're looking at the part of this curve that moves from the point 1, -1. So that is from this point. We are moving along this curve to the point 1, +1. So this would be our curve C. Now, if we want to evaluate this line integral, we know that we need parametric equations for our curve. So here for a plane curve, I need x of t and y of t. So let's start by finding these parametric equations for the curve C. So here they would be given by, well, x was defined as y to the 4th. So if I choose y to simply be t, then x, which is y to the 4th, would be t to the 4th. And then let's think about the range of values for t. So here we're ranging from the point 1, -1 to 1, 1. So that first point 1, -1 has a y value, or a value of t, of -1. And the second point has a value of t of +1. So our range of t values would be from negative to +1. So let's see if we can set up an integral for the line integral we're given here. So the one we were given was the integral over the curve C of xy with respect to x plus x minus y with respect to y. So setting this up as an integral in the parameter t, we would be integrating over the t interval from -1 to +1. And the first part of our integrand was x times y. So for points on our curve, x was t to the 4th, y was t. And then our differential of x, this term here, well, x was t to the 4th, so we're going to multiply by its derivative. That is 4t cubed times the differential of t. Then we add, for the next part of it, we had x minus y, so that is t to the 4th minus t, times the differential of y, dy. Now here y was equal to t, so dy is then just 1 dt. So let's see what we have here after we simplify a little. We've got the integral from -1 to 1 of, expanding our first few terms, we have 4t cubed times t to the 4th times t, which gives us 4t to the 8th power, then plus t to the 4th minus t, all times dt. I can factor out that common differential dt from each term. So now we just have a regular definite integral to evaluate. So we could find our antiderivative, which would be 4/9 t to the 9th plus 1/5 t to the 5th minus 1/2 t squared, evaluated from -1 to +1. So plugging in t equals 1, we have 4/9 plus 1/5 minus 1/2, and then we subtract what we get when we plug in -1. So plugging in -1, we have -4/9 minus 1/5 minus 1/2. So here we can see when we combine these, our -1/2 minus the -1/2 will cancel. We're left with 4/9 plus 4/9, or 8/9, plus 1/5 plus another 1/5 is 2/5. So this gives us 58 over 45 for this integral. So we see in this example, okay, we can define a line integral of a function with respect to x or y, or maybe we have a line integral that we're integrating over a single curve c, but we're integrating different functions with respect to different variables along that curve. So in the next part of this section, we'll consider some examples where we'll see that the orientation of our curve may affect the value of our line integral depending on which variable we're integrating with respect to. So to illustrate this, in this next example, we're considering the line integral of y squared with respect to x plus x with respect to y over the curve c, where in part A, C is the line segment from the point 0, 0 to the point 2, 4. So here in part A, let's visualize our curve. We have in the xy plane a line segment moving from the origin 0, 0 to the point 2, 4. So here we're moving from 0, 0 to the point 2, 4. So our curve is this line segment being traced in this direction. And to evaluate this, we need to find parametric equations for this line segment. So here our line segment is moving from the origin to the point 2, 4. So its direction vector would be 2, 4. So parametric equations for the line segment C are given by x equals, well, we started at 0, 0, and our direction vector was 2, 4. So x is 0 plus 2t. Y is then 0 plus 4t, or just 4t. And we're moving from 0, 0, so that corresponds to t equals 0, to the point 2, 4, which would correspond to a value of t equal to 1. So once we have these parametric equations, we can set up our line integral as an integral in terms of the parameter t. So here we had the line integral over c of y squared dx plus x dy. So this becomes an integral with respect to t on the interval from 0 to 1. The first part of our integrand was y squared. So here y was 4t. We're squaring that. Times the differential of x, which in this example, the derivative of x is 2, times the differential of t. And then we add x, which was 2t, times the differential of y. So here y prime is 4 times our differential of t to get dy. So simplifying this, we have the integral from 0 to 1 of, when we square 4t, we have 16t squared times a 2 gives us 32t squared, plus our 2t times 4 gives us 8t dt. And then to integrate this, we find our antiderivative. So in this case, 32 over 3 t cubed plus 4t squared from 0 to 1. So this then gives us 32 thirds plus 4 minus 0 when we plug in 0 for t. So we have 32 thirds plus 12 thirds would give us 44 over 3. Okay. So we get 44/3 for the line integral of this function over that curve. So let's look at the next part of this example. In part B, we are asked to integrate that same line integral. So here for reference it was the integral of y squared with respect to x plus x with respect to y over the curve C. And in part B, we're changing our curve slightly. Here, C is the arc of the parabola, y equals x squared, from 0, 0 to 2, 4. So here, our curve would be the curve going from the origin to the point 2, 4, so it's connecting the same endpoints as the example we had in part A, but it's no longer a line segment. It is the arc of a parabola, y equals x squared. So this parabola opening upward, traversed in the similar direction from 0, 0 to 2, 4. So we might ask, well, this curve is a different curve in the xy plane, but it connects the same 2 points. So will we get the same value for this line integral or a different value? So let's test it. In order to evaluate this, we need to parameterize our curve C. So in part B, parametric equations for our curve could be given by taking x equals to t, and y is x squared, so we would have t squared. We're moving from the point 0, 0, which would correspond to t equals 0, to the point 2, 4, where t is 2. So let's set up our integral for this line integral with respect to t. So in part B, we're integrating over the t interval from 0 to 2. And our function was y squared, so y is t squared, we're then squaring that, times the differential of x, which would be 1 dt, plus x, which is given by t, times the differential of y, which in this example is 2t dt. So simplifying this, we have the integral from 0 to 2 of t squared squared, which would be t to the 4th, plus t times 2t gives us 2t squared, all times dt. That common differential I can factor out. So now we just have an integral with respect to t, so we find our antiderivative, which is 1/5 t to the 5th, plus 2/3 t cubed from 0 to 2. So plugging in 2 for t, we have 32 over 5, plus 8 times 2/3 is 16/3, minus, when we plug in 0, we have 0. So we are left with 176 over 15. So this is not the same expression that we had in part A. So even though our curve connects the same endpoints, since it was not the exact same curve, we had different values for x and y along this curve, so it affected the value of our integral. So maybe as a note here, this is different from the result that we had in part A. So just because a curve connects the same 2 endpoints does not necessarily mean that the line integral will give us the same value. Now there are certain conditions where that will be true, and we'll see those conditions a little bit later in chapter 6 when we talk about line integrals of vector fields. Then in the last part of this example, part C, we're asked to evaluate the same line integral. So again, that was the integral of y squared with respect to x plus x with respect to y over the curve C, where in this part, C is the line segment from the point 2, 4 to the point 0, 0. So here, our curve is the line segment which passes from the point 2, 4 to 0, 0. So it is the same curve that we were considering in part A, but traversed in the opposite direction. So we ask ourselves, well, is this going to affect our answer? So in order to address that, we need to find parametric equations for this curve. Now here, our direction vector for this line, well, we're moving from 2, 4 to 0, 0. So our direction vector would be -2, -4. So parametric equations for this line segment, we could define by taking x as our initial x value, which was 2, and then our direction vector was -2, -4, so we would have -2t. And for y, we would take our initial y value, which was 4, minus 4t. And here we were moving from the point 2, 4, which would correspond to a parameter value t equals 0, to the point 0, 0, which would correspond to a t value of 1. So let's see if we can set up our integral in terms of t for this desired line integral. So here again we had y squared with respect to x plus x with respect to y. Here we give this as the integral from 0 to 1. Our y value was given by 4 minus 4t. We're squaring that quantity, times the differential of x, which is -2 dt, then plus x, which is 2 minus 2t, times the differential of y, which would be -4 dt. So we have the integral from 0 to 1 of, if we expand this, let's see what we have. So let's see how I want to do this. We could proceed in the following way. From this first term, where I have 4 minus 4t quantity squared, I can factor out a 4, but remember it's being squared. So here we're actually factoring out a 16 times this -2 term. So 16 times -2 would give us a -32. And when I factor out a 4 from that term, I'm left with 1 minus t quantity squared. Now in a similar way, from this next term, I could factor out a 2 from the 2 minus 2t, and then I would have a 2 times -4, which gives me -8, times a 1 minus t, all times dt. So let's see what we get. We could factor out a 1 minus t from each term, but in either case, I think we'll eventually have to expand to integrate. So let's see what we have here. Integral from 0 to 1 of -32 times, when we expand this, we have 1 minus 2t plus t squared. And then distributing the -8, we have -8 plus 8t dt. So this is the integral from 0 to 1 of, let's see what we're left with. So distributing the -32, we have -32, then -8 gives us -40. Then -2t times -32 gives us 64t plus 8t. So altogether 72t. and then minus a 32t squared dt. So if we find our antiderivative, we have negative 40t plus 72 over 2t squared minus 32 over 3t cubed from 0 to 1. So we are left with a negative 40 plus 72 over 2, or 36, minus our 32 thirds, minus when we plug in 0, we get 0. So simplifying, we're left with negative 44 over 3. So notice if we compare this result with what we found in part A, we found our line integral over this curve C was 44 thirds. And in part C, the line integral over the same line segment in the opposite direction gave us the negative of the value that we found in part A. So here, as a note, that this is the negative of result for part A of this example. So what we're illustrating in this example was the following. In general, the value of a line integral depends not just on the endpoints, but also the path and the direction in which our curve was traversed. So it doesn't depend only on the endpoints of the curve, but it could be affected by the path itself along as well as the direction of our curve. So some results that we can describe here about the orientation of our curve and how it affects the value of our line integral are the following. So here, let's suppose that we have a parameterization of some curve. So we have a space curve whose parametric equations are x, y, and z of t, where our parameter t ranges between two values a and b. So this parameterization determines an orientation of our curve C, where the positive direction corresponds to increasing values of t. Now the curve which has the opposite orientation of C can be denoted as negative C. So like the curves that we saw in part A and part C of that last example. They were the same sort of curves but with the opposite orientation. So a relationship among the line integral over a curve traversed in the opposite direction and the original curve is described by the following. If we're integrating a function over a curve taken in the opposite direction, with respect to x, y, or z, we get the negative of the line integral over that same curve traversed in the positive direction. We saw that result from comparing parts A and part C in that last example, and it happens that it holds true in general, not just for that specific example. But one thing to be a little bit careful of is if we are evaluating the line integral over a curve with respect to arc length, the order that we traverse that curve does not matter. If we traverse it in the opposite direction, we get the same value as we would if we were to integrate that line integral over the same curve taken in the forward direction. So here, if you integrate with respect to arc length, the orientation of your curve doesn't matter. If it is an integral with respect to x, y, or z, then orientation will affect the value of this line integral. So let's look at an example where we'll evaluate a line integral with respect to x, y, and z over some space curve. So in this next example, we are asked to evaluate the line integral of y with respect to x plus z with respect to y plus x with respect to z over the curve c, which is given by the vector function t to the fourth t cubed t to the fourth on the t interval from 0 to 1. So it is a curve which connects the origin 0, 0, 0 to the point 1, 1, 1. So to evaluate this line integral over the curve c of y dx plus z dy plus x dz, well, let's transform this to an integral in the parameter t over the interval from 0 to 1. So here the first part of our integrand was y. Now our y parametric equation for this vector function is t cubed times the differential of x. Now here x is t to the fourth, so dx will be 4t cubed dt, plus for our next term we had z, which is t to the fourth times dy, which here is given by 3t squared dt, plus x, which is t to the fourth times dz. So the derivative of that last component would be 4t cubed. We multiply by the differential of t. And so let's see what we're left with. We have the integral from 0 to 1 of, for our first two terms, t cubed times 4t cubed gives us 4t to the sixth. We have t to the fourth times 3t squared. So that gives us a 3t to the sixth. And for this last term, t to the fourth times 4t cubed, that gives us a 4t to the seventh, all times dt. So combining these first two terms, we have the integral from 0 to 1 of 7t to the sixth plus 4t to the seventh dt. So our antiderivative is then t to the seventh plus 1/2 t to the eighth from 0 to 1. So plugging in 1 for t, we're left with 1 plus 1/2 minus plugging in 0, we have 0. So altogether 3/2 would be our value for that line integral, where we're mixing our variables with respect to x, y, or z all in the same integral. All right. So in the last part of this section, we will start to talk about a line integral, no longer of a function of two variables, but a line integral of a vector field of 2 or 3 dimensions over some curve in the plane. And we'll think about what this might be used to represent physically. So in this last part of our section, let's define a line integral of a vector field. So here's how it's defined. If we have a function f, which represents a continuous vector field, which is defined on a smooth curve C, which has a vector function description r of t for t from a to b, then the line integral of the vector field f along the curve C is denoted in the following way. So we would have an integral with the subscript c to denote the curve that we're integrating over. The vector field that we're integrating is this capital F vector function, could be in 2 or 3 dimensions, dot dr. So here, the way that we can evaluate this line integral of a vector field over some curve is again to think about transforming this to an integral in terms of t. So here our parameter interval t describing the curve was from a to b. And the way that we're going to define this is by taking my vector field f and replacing x and y, or x, y, and z, by the values of x, y, and z given by the component functions of that vector function, r of t, which describes my curve. And then we are taking dot dr, so we are taking a dot product then with the differential of r, which would be given by r prime of t dt. So here, if our vector function was r of t, we would say that dr dt, the derivative, is r prime of t. So the differential of r is then r prime of t times the differential of t. So we can convert a line integral of a vector field to an integral over that parameter interval t, making use of this definition. In this integral of a vector field over a curve is sometimes called the circulation of that vector field along the curve C. Circulation, sometimes also called flux, but we'll define another expression for flux a little bit later in this chapter. So here we use circulation for this integral of a vector field over a curve. So let's look at one example of this, and then we'll think about what this line integral of a vector field might represent, how we can think about it. So in our first example, we're asked to evaluate the line integral of f dot dr over the curve C, where our vector field f is the field whose component functions are x squared y and negative xy, and the curve C is the curve whose vector equation is t cubed t to the fourth, where t ranges from 0 to 1. So in order to evaluate this, we need to find a couple of things. The first is going to be my vector field f as a function of t instead of x and y. So x and y we're going to replace by the component functions of r and t. So here the first component of our vector field was x squared times y. Now x, for points on our curve, is given by t cubed. So we have t cubed squared times y for points on this vector function are given by t to the fourth. And then our second component for the vector field was negative x times y. So here we have negative t to the cubed times t to the fourth power. Or this can be simplified as, for our first component, t cubed squared would be t to the sixth times t to the fourth, so t to the 10th, and then a negative t to the seventh. So we need to find f in terms of the parameter t, and we also need to find the derivative of r, that is r prime of t. So in this example, r prime is given by 3t squared 4t cubed. So in order to evaluate this circulation, that is the line integral of f over the curve r, we would integrate with respect to t over our t interval, in this case from 0 to 1, was given in the problem statement. And we're taking f of r of t dot r prime of t dt. So that is the integral from 0 to 1 of, let's see what we get for this dot product. So taking the product of the first components of those two vectors, f of r of t and r prime, we have 3t to the 12th power. And then we add the product of these second two terms of these vectors, which would be negative 4 t to the 10th power, dt. So let's see what we have. Evaluating our antiderivative, we end up with 3/13 t to the 13th minus 4/11 t to the 11th power, evaluating from 0 to 1. So plugging in 1 for t, we have 3/13 minus 4/11. Minus, when we plug in 0 for t, we get 0. So this simplifies to, we're left with a negative 19/13 times 11, whatever 13 times 11 works out to. So let's see, what is that? 30 plus 13, 143, and negative 19/143, I believe. So this would be the line integral of that vector field evaluated over that curve C, whose vector function is given. So let's think about what exactly we're doing here. So to think about this geometrically, let me go back to our previous section of notes, the section 6.1 material, where we were plotting some vector fields, and think about what a line integral might represent over a curve. So let's suppose that we were working with the vector field shown in this first example. The line integral of a vector field over a curve can be thought of as the following. So let's say that this was the plot of our vector field shown in red, this little direction field. And we have some curve in the xy plane. We'll call this curve C, which is described as the graph of some vector function. So what this circulation or line integral of a vector field represents is the following. We're adding up the values of our vector f of xy over all points, or we're adding up the magnitude of these vectors over all points along this curve C. So we see if we have a curve C, which is traversed in the same direction of motion of our arrows, if we're adding up all these positive values for the values of our vector field, f of xy, then our circulation would be positive. However, let's say that we have a curve which is being traversed in the opposite direction of our arrows. So let's say I had a curve that looks something like this. I'm traversing my curve in this direction. Let's call this maybe C1 and C2. This second curve is moving in a direction opposite of the direction of the arrows for my vector field. So it would have a negative value in this case. Now the way that we can think of this as a physical interpretation would be if this vector field represents, say, a velocity field, maybe fluid velocity for fluid moving through a plane, and we have some object, say a boat, or some object traveling through the water against the current, we could think about this vector field as representing the work done by that vector field in moving our object along this curve. So of course, if our force or velocity field is moving against, or if our object is moving against the direction of the velocity field, the work done by that field would be negative, since our object has to overcome it. However, if our object is moving with the direction of the current, we would have a positive work done by that vector field in moving an object along that curve. So for the second example here, where we've got this vector field, if we were to consider a curve that described the path of an object moving in this direction, we would think that the line integral over that curve, let's call that curve C1, of this vector field with respect to r would be a negative value. However, if I were to look at a different curve, let's say an object which is moving along this path in the indicated direction here, call that curve C2, the line integral over that curve of this vector field would be positive since our object is moving with the direction of this field. All right. So here's a sort of a physical interpretation of this line integral of a vector field. If we think about plotting our vector field in our curve as describing the motion of some object through that field. So let's go back to our section 6.2. So let's look at another problem sort of similar. We have here the line integral of a vector field f over the curve C, where f is now a three-dimensional vector field, f of x, y, and z, and C is a space curve defined by r of t is sine t, cosine t, t squared from 0 to 1, so part of a helix here. So to evaluate this line integral, there's a few things that we need to find. The first is the value of our vector field for points along this curve defined by r of t. So here, our first component of the field is x squared. Now for points on the curve, x is given by sine of t, so we have sine squared t. Our second component is x times y, so here we have sine t cosine t. And our third component is z squared. Now z is t squared, so we have t to the fourth for that last term. And we also need to find r prime of t. So differentiating our component functions, we have the derivative of sine t is cosine t, derivative of cosine is negative sine t, and derivative of t squared is 2t. So the definition of this line integral of our vector field over that curve, well, we set this up as an integral with respect to t from 0 to 1 of the dot product of f of r of t with r prime of t dt. So this becomes the integral from 0 to 1 of, if we look at the product of our first terms, we have sine squared t times cosine t. Then we add the product of negative sine t with sine t cosine t. So that gives us negative sine squared t cosine t. And then the sum of the product of our last two terms, we have 2t to the fifth dt. So we see here our first two terms cancel, and we are left with just the integral from 0 to 1 of 2t to the fifth dt. So our antiderivative is then 1/3 t to the sixth from 0 to 1, which leaves us with a constant 1/3. All right. So in the last part of this section, we can summarize what we had described as the representation for this line integral of a vector field over a curve in terms of a physical application and finding work. So here we can think of defining work as a line integral in the following way. So let's suppose that we have some vector field f, which is a continuous field in space, and it represents a force acting on an object at a point in space. So this would be an example of a force field, a vector field representing force acting on an object at a given point. So maybe it could be, say, force acting on an object. If we think about this as maybe a velocity field for a fluid, well, the velocity of our fluid is then pushing an object in a given direction, so we could think about the force imparted on an object by that velocity field as an example of this. And then we could think about the work done by that force field F in moving some particle along a smooth curve C through space, which is defined by a vector function r of t from t equals a to t equals b. And this work would be given by the line integral of that vector field over the curve C. So in our last example, we are asked to find the work done by the force fields given here, whose component functions are xz, xy, and yz, acting on a particle that moves along a curve in space defined by t squared negative t cubed t to the fourth for t equals 0 to 1. So again, there's a few things that we need to find to evaluate the line integral of a vector field. The first is to get that vector field in terms of the parameter t. So in this example, our first component of that force field is x times z. So here we would have t squared times t to the fourth, so t to the sixth. Our second component is x times y, so multiplying the first two components of r, we have negative t to the fifth. And our last component for the field is y times z. So multiplying our last two components for r, we have negative t to the seventh. And we also need to find r prime of t. So here, r prime of t is given by 2t, negative 3t squared, and 4t cubed. So now we're ready to find the work done. The work is found by taking the line integral of this force field over the curve C. And to evaluate this, we set up the integral over our parameter interval from 0 to 1 of the dot product of f with dr. So multiplying the first two components, t to the sixth times 2t, gives us 2t to the seventh, plus negative t to the fifth times negative 3t squared, gives us a positive 3t to the seventh. And our last two components multiplied gives us a negative 4t to the 10th dt. So we have the integral from 0 to 1 of 5t to the 7th minus 4t to the 10th dt. Or evaluating the antiderivative, we have 5 over 8 t to the 8th minus 4 over 11 t to the 11th from t equals 0 to 1. So this leaves us with 5 over 8 minus 4 over 11 minus 0 when we plug in 0. So we are left with altogether 55 minus 32 leaves us 23 over 88 for the work done by that force field in moving a particle along this curve.